So, when we start, and now I made the questions bigger, so maybe that helps. Everything we touch in the universe is considered matter. The table, the car, the clothes we wear, even our own body. So listen to this. Water is a good example. For once, we are made of a lot of water. We learned about here's water, or should be water. Also, it comes in different forms depending on its temperature. Below 0 degrees Celsius, I know we do Fahrenheit here, but there's this thing called Celsius. Have you heard of that? Good. It's scientifically, it's an easier one to measure than Fahrenheit because 0 Celsius is when the water freezes, and 100 degrees Celsius, freezing is ice, is when the water becomes steam and it starts boiling. What are the three states of matter called? So that's a good example. Matter has three states: a solid state and gas state. Good. There you go. Question number 1. All good. There we go. There are the different states. The reason why we're going to talk about water. Water is a really cool molecule. We probably, for our purposes, mostly use this concept in water for us. But we need to know about it. Energy manipulates matter. For example, a tea requires heating of water. It is energy such a form of a stove that will do that. Energy is flowing and hard to contain. If it's in action, we call it being kinetic. That's action. Right? If it is stored for later use, it's potential energy. Give us some example how that applies to your body. Potential energy versus kinetic energy. The who? Fat. Fat's a very good battery thing. Yeah, that's the potential energy. It's a storage of energy. Glycogen is also a storage of energy. It's a storage of glucose. It's short storing. We don't store it. We have long-term storage in fat and short-term storage in glycogen, which we have in liver and in muscle and a little bit in the brain. Helps us get energy quite quick. Which is okay. Anybody else? How about kinetic energy? Walking, running, all that kind of stuff. All the stuff we do. Thinking. That's actually kinetic energy too. Thinking? You need ATP to think. You're going to use a lot. If you study for a few hours, you'll be hungry. Otherwise, I'm wondering if you study that.
What is ATP?
ATP is an energy molecule, and we have a slide on it, but it's going to be on Wednesday. It's an energy molecule. It's the energy molecule for the body. It stands for, you don't have to write it down, it's on the slide, adenosine triphosphate. So it's just a molecule for us, a chemical composition that has a lot of energy in it. And when we clip off one of the pieces of the molecule, we get a lot of energy created. So we use it as the universal fuel, the universal energy. No, it's the energy molecule. The fuel is more the sugar that we eat, the glucose. How does your energy comes in different types? How does your body use chemical energy, for example? Huh? Metabolism. Chemical energy is in the food molecule. Break down a food molecule, you get chemical energy out of it. What about which system uses electrical energy? The nerves. So if you ever hit your funny bone, that's the nerve energy. That's like electricity shooting down your arm. There you got it. It is actually the same as electricity. It is electrons that are flowing around. So we'll talk about that. How about mechanical energy? Muscle building. Yep. All the crazy people going to the gym all the time. Well, you know, nerves talk to nerves. Nerves are things that convert information to something else, right? They process information, but they either attach to other nerves, they attach to glands, or they attach to muscles. And the brain is actually just a whole bunch of fine nerve endings, a lot of nerve endings, a lot of stuff going on up there. And if we have a lot of anxiety, for example, we have a lot of activity in there, what we got to do with it? We got to do something with it. And that's a lot of times is when we can do exercise, it calms us down. It helps dissipate that energy. And so exercise can be very helpful mentally for that purpose. Of course, we can kind of overdo it too. And too much output energetically is also not necessarily that great for the heart. It depends. Changing the type of energy is generally smooth. For example, you can get potential energy in your muscle becomes kinetic, mechanical energy as soon as you or the brain decides to move. Energy conversion produces a byproduct that the body can make good use of. For example, maybe sugar we can get more. Or at this table, what is that byproduct? Heat. That's when you are cold, if you do jumping jacks, or when you start walking, you know, I should have put on this jacket, and then you walk a little brisk, and in a few minutes you don't remember anything of that. It's all cool. That's the heat. So it's a loss. Like if you're thinking of the light bulb, right? Because it's just the old light bulb, you screw it in, it gets hot, you can heat up a room, but all you really wanted was the light. And so it's a waste. In the body, it's also a similar waste product, we call it, but we use it to create other body processes, integrate it, use it to our benefit. So that's the heat thing. There you go. And a lot of these things you like the pictures. Big one there.
Yeah, how is that radiant? Kind of
The
in our body.
Well, it's visible light. That's the radiant light comes in and then transfers into electrical energy and brings to the brain in terms of seeing. I just like that picture, so I put that one on. I know. And there's the energy conversion where we lose the heat. The light bulb is a very easy good example to understand. Whoa! Now let's look at these. So let's go back to matter and understand a few things of how it is made up. Oh, this is good. This is where we get into the meat of the chemistry stuff. The universe is made of many different elements, and I just heard that we found one more metal that we created with compressing hydrogen as hard as possible, and somehow it became a metal, which has a lot of uses potentially. But these elements need to be studied, because we need to understand how they work, how they behave, and of course, to understand that, we want to get an understanding how they're made up. And so we're looking at the smallest possible piece that we can look at, or try to look at, to understand how the universe is made up. And what do we call one of these fundamental pieces of an element?
Atoms.
Atoms. And so atoms means we can no longer divide it. It's non-dividable. Although, of course, we figured that that's not necessarily the case, but that's what we go with. And believe me, for our purposes in biology, the old way of looking at all this is just fine. Structurally, the particles are made up of similar to our solar system, or at least that's what we think of. There is a center, which is a nucleus. It's kind of like the sun. And then there are things, we're not sure if they're really physical particles or they're just energies that are floating around that center in different fields or orbits, they call them, like in our orbits. What do we call the three tiny substances that make up the nucleus and the orbit? Protons, neutrons, electrons. Good. You already know this, huh? And then the next thing about this atom thing is that many things in our universe, in our world, are made based on two opposites, like night and day, hot and cold, all that duality. No, I won't say that. Atoms are structurally held together by the interaction of charges. So we got a positive charge, we got a negative charge. The positive attracts the negative. The positive repels the positive. The negative repels the negative. I should show a little bit of a video that I made of my granddaughter when she puts magnets on the fridge. And she learns that she learns how to pull them off, not slide them down. And then when she puts them on wrong, they don't stick. The first one falls down, and then she realizes which one holds and which one doesn't. So that's, that's fundamentally how our atoms are made. Which part of the atom is positive? The protons. And then the negative is the electrons. And the neutrons, why is this wrong? Oh, see, that's out of order. The neutrons are neutral. But it ain't a neutron. That's a neutron. So we have protons, they have weight and a positive charge. Then we have neutrons, they have no charge, but they have weight. And then we got these little small tiny things that we don't even know if they're really things or just energies. They're electrons, they're just negatives. So they have not really any weight to them. They just sort of have an energy to them. Again, just so you can understand that a little bit. And then this was out of order. Combining atoms with one another makes molecules. Water, for example, has 3 atoms combining, 2 hydrogens and 1 oxygen. How, is this the right question? How do those atoms combine is interesting. Which part of the atom? No. Did I miss a question? It's bonds, right? It's about bonds. And which part of the atom creates a bond with the other part? The electrons. So that's the next step. So as we, I'm sorry, I'm a little out of sequence, sorry. But as we get through understanding the atom, and then atoms combining with other atoms, what they do is they make molecules when they do that. So, and the molecules are connected by interactions between the outer shells where the electrons are in. The molecules are not connecting the nucleus to one another. They're connecting the electrons to one another. It's kind of like you're holding hands with somebody, you're not hugging with them. It's like you're not, the core doesn't hold together. The outside holds together. And so it's the bond that's important. And now we get to this, right? And so when we look at further making these connections between different atoms, we have to look at these shells a little bit more. Because actually the connection shell is the outermost shell. And what is the outermost shell, what is the outermost orbit of an atom called? The valence. And in an ideal situation, the outermost shell, and this is not fully accurate, it doesn't go for the lower level atoms, but for the up at some point it goes for that. The outermost shell wants to have 8 electrons in it. We call that octet group. So if they have 8, they don't react. If they don't have 8, they will have the potential to react. Then we have a situation in an atom where the charges, the nucleus, and the electrons, they're always sort of in equal. Otherwise, it's a charged molecule, a charged atom, but it's not. We don't normally just walk around with a charged atom. But if their outside shell, for some reason, because the numbers don't add up, does not have 8 electrons in their outermost shell, those atoms become reactive atoms. They're not quite satisfied. That outside shell is not quite full. Even though the charge is complete, that's fine. But one thing doesn't, is not quite complete. But the ones that are having 8 in them, they're fulfilled, they become stable or non-reactive. What do we call those? Inert elements. So they don't react.